we're going to introduce you to the NewLib library and its application to multi-level large-scale solar field models. So multi-level, it's the level of detail of the models, and large-scale is basically more than 5,000 square meters of collectors. So this work has been in collaboration with the CEA, and Alexis and I are from NewHeat.
Okay, so maybe first I'm going to introduce what we are, NewHeat as a company, and what we do. So what is our objective? What is our aim? Actually, heat is half. It's half of the problem when you think about decarbonizing our global energy consumption and supply. So half of the final energy consumption is related to heat, and 75% of this heat is supplied by fossil fuel means. And half of it is consumed by industrial processes and district heating application. So large-scale heat consumer, and this is the application we try to target at NewHeat. What do we propose to address these heat requirements, these heat needs? We propose to offer local and sustainable heat production systems based upon technologies, a mix of technologies that we are going to investigate and deploy in this presented order. So we will always look at heat recovery opportunities. Afterwards, looking at solar thermal possibility within the context of the client, looking also at geothermal perspectives, and at the end of our merit order cycle, looking at biomass generation technologies or biogas. We aim to support those renewable heat production systems with a controlled and optimized electrification in mind, so meaning like the deployment of heat pumps in our systems. And of course, at the heart of our systems, we always introduce thermal storages that allows to connect those heat production system and to balance the offload with heat consumption from our clients. And now, how do we deploy this renewable heat production system? NewHeat is an integrated and independent heat provider, meaning that for each project, we design, we develop, we build, and we operate the renewable heat plants over a period of 20 to 25 years. At the heart of of our activity is also the financing of our projects, meaning that we own the renewable heat plant that we built, so that our relationship with our client is actually the setting up of a heat supply contract over this period of time. And so this positioning is an incentive for us to offer optimal technological solution in terms of mix and guarantee long-term performance of our plants. So the different activities and jobs that we pursue at NewHeat, so the design activities, the development activity, the construction activity, and the operation one, creates some modeling needs at every step of the life cycle of a project at NewHeat. Especially, for example, in the preliminary phases of our project, we need to use simple models to investigate different configurations. For example, in between the different renewable heat production technologies that I presented you before. Once we have validated the interest of our client and then we have signed a first contract, we're able to go into detailed engineering, where we will employ more detailed models, where we'll be able to size each component. And of course, once the plant has been put into operation, we will try to build some digital twins to have like a way to have a live comparison of the real performance of the plant to what was expected, and allows us to see any potential deviation of our offset. And once again, just putting a lot of emphasis of the different jobs that we do cover at NewHeat, but the financing aspect is the key one here, because as the plant owner, we want at every step of the way, we want to estimate what will be the impact on the profitability of our projects. So whether you make a decision to switch a configuration at the early steps of the project, or you made a dimensioning decision during the engineering phase, or if you want to estimate the impact of the of an operational control decision, you need to see what will be the impact on the profitability of the project. So this leads us to the objective to always take every technical decision with the idea of estimating what will be the impact on the final heat production, for example, over a typical year period, so that we can at first determine the heat price, like to set up our heat purchase agreement, and afterwards estimate the potential impact on the profitability of the project once the heat price has been set for the contract. So to cover those very different needs in terms of modeling approaches and details, we thought at NewLib that Modelica could be a good solution to cover these needs during our different steps of the project. So we went that way already 3 years ago. And one of our first steps, because as you've seen, we are deploying renewable heat solutions. So by looking at renewable heat production system and consumptions, one of the key problematic is to model thermo-fluid systems, so coupling flow, water flow, or coolant flow, and temperature situations. So to do so, we had to select what will be the correct, in Modelica, what will be the correct way to do the fluid simulation. Sorry. So our first step was to select the correct, as I said, the correct fluid library to ensure that it will sustain our needs on the long term. So after doing like an internal benchmark, we selected the new, but you might have heard about already, the thermo-fluid stream library to build as a base library for our own specific library that will be able to simulate our renewable heat plants. So here I'm jumping a bit ahead in the presentation actually by showing you something that Igor will present you in detail afterwards. So this is, for example, on the left, it's kind of messy, but still it's a representation of one of our upcoming projects, one of our upcoming renewable heat plants that will be dedicated actually to industrial process. In that case, it's going to be a malt house, just for information. And so what we like to show here is the kind of complexities that those new renewable heat systems can achieve to cover like a global heat supply to a client. So for example, we have designed a system where we have one large-scale solar field, 2 industrial heat pumps, 1 large thermal energy storage in the form of a tank, multiple buffers. We have a heat recovery system on the exhaust air of the malt house. The malt house also requires a cold production. And there is, to do so, we supply heat to the malt house through 2 interconnected heat networks, and there is 5 integration points, so 5 heat exchangers directly within the process. So it's kind of a fairly complex architecture, as you can see, in terms of thermohydraulic problematic. But we were able to achieve like reliable simulation capabilities on these systems through the use of thermo-fluid stream as a basis for library, because you might recognize on the right the famous translation log. And you can see in this is the translation log of this system, and there is actually 0 nonlinear system for this model. So that's a good sign of reliability in terms of calculation. So yeah, so really one of the main advantages is the absence of nonlinear system, thanks to the use of thermo-fluid stream, and also, in addition, it allows us to handle multiple fluids, and which are in different phases. You can handle liquid, gas, or vapor liquid equilibrium, which allows us to cover the whole spectrum of renewable heat solution with peace of mind, let's say. So now with that out of the way, I will let Ingro introduce more in detail what we did for creating NewLib and how we use it already today to model our existing plants and our upcoming plants, such as this one. Thank you.
Yeah, but we have a more simple project than this one. As Alexis said, so we developed the NewLib library to fulfill all our modeling needs for all the phases of our projects. So the NewLib library is a proprietary library that we developed within the Dymolaenvironment. And this library is based on thermofluid stream. And it is dedicated to the dynamic modeling of the renewable heat production, recovery, and supply systems that we have at AtNewheat. So what you can see on the left is the main packages that we have in the library. So the starting one, let's say, is the component package. So where you can find all the component, the physical component that we need to model our renewable heat production plants. So you have solar fields, heat pumps, boilers, thermal storage. So you can have a tank thermal storage, or you can also have pit storage for bigger projects. We have also heat exchangers, actuators as pumps and valves, pipes, dry coolers, and heat tracing. So all those components can be either in a simple modeling type, so for the early phases of our project, for design phases. So we have simple models, but we also try to develop more detailed models for engineering phase, for example, for sizing phase of the component in our project. And after that, the main packages that we have is the control package, just right after the components package. So we work a lot on control at NewHeat. So we have to develop blocks of high-level control. The high-level control in our plants define the functional modes of our systems. For example, for a solar field, you can be either in production mode. If there is sun, you can provide heat to the storage, or you can be in preheating mode. So it means that you're not high enough in temperature, so you have to loop bypassing the heat exchanger to warm up the solar field. So this is what the high-level control does. And we have also low-level control blocks that activate the actuator to fulfill the needs of the different modes that we have in our plants. So this is basically the two main packages that we have in our library, and we are also working on a typical config package that I will present you just right after. And as Alexis said, the main objective of our modeling is to see the financial reliability of our project. So we also have an economic package to calculate the heat price and the levelized cost of heat, for example. So as Alexis said, we need to fulfill a lot of modeling needs for all phases of our projects. So we want all of our engineers to use our Modelica models in a perfect world. But we know that this is very challenging, and it can be not straightforward for an engineer that is not used to Modelica to use our Modelica models. So that's why we developed the typical config package in the NewLib library. So the aim of this package is to propose typical configuration of our plants to engineers, so they don't have to go through modeling component by component our plant when they design one. So you can see on the left is a typical component by component modeling of one of our plants. And what you see on the right is doing the same thing, but using what we called subsystems. So it's functional systems in our plants. So you can see the solar field subsystem, the storage subsystem in the middle, and then the consumer subsystem. So it makes it easier for the users to parameterize the simulation, and it makes it more error-proof because we already put a lot of automatization in the parameterization of those models. And one last thing is that from these templates, from this subsystem that our engineers can use, you can also go from simple models in the components to more detailed one. So all of our components model in the subsystem are switchable. So you can switch from, for example, a simplified representation of the solar field to a more detailed one when you go through the phases of your project. And this is what I'm going to show you now. So this is two modeling approach that we have for the solar field representation in NewLib. On the left, you can see the simple modeling of the solar field, even if it doesn't seem that simple, but it is simple as it is only one thermal node. So you can see on with the blue circle at the middle. So it's only one thermal node based on the performance equation from the ISO 9806. And then the pressure loss is calculated by considering an equivalent solar field. So we don't represent the exact hydraulic configuration of the solar field. We just consider an equivalent rectangular solar field, and we calculate the most constraining path in this configuration to calculate the pressure loss of the solar field. And then on the right, you can see a more detailed solar field. So on the thermal port, we have a n-row nodes approach. So we represent each row of solar collector in our solar field. But the number of solar collector in each row can be different. And then we represent into detail the hydraulic configuration of the solar field with manifolds, with valves, elbows, etc. So you have a very detailed representation of the hydraulic in the solar field. So now to finish this presentation, I'm going to show you a validation test case that we made with those two kind of models that we have for the solar field in NewLib. So at AtNewheat, we have actually 6 operating plants, and one of them is called Narbosol, who is in the city of Narbonne in France. So it's basically it's a solar field, a large-scale solar field, providing heat to a heating district network for the city of Narbonne. And as you can see, we have a tank thermal storage. So what is very nice at AtNewheat is that we have operating plants and we have measured data on our operating plants, so we can compare our model to live data of our plants. And this is pretty cool when you do modeling. Sorry. So the last slide show you the result of the comparison between our models and the measured data from Narbosol in September 2024. So on the left, you can see the configuration of the model that we used. So you can see that we have the solar field model with inlet pipe and outlet pipe. We have a flow generator to impose a mass flow rate to the system. And we have an inlet from the TFS to impose the temperature at the inlet of the solar field. So we are using both the simple representation of the solar field and the detailed one, and we compare it to the measured data of Narbosol. And so what we can say is on the energy part, so the first graph, you can see the energy provided by the solar field on the whole September month for both model and the measured data. So this is pretty good for both model, with less than 3% error for the two models. And you can see in further details this in graphs 2 and 3 here. So this is the thermal power transmitted by the solar field to the fluid for 2 typical days. So graph 2 is a sunny day, and then you have a cloudy day. So it's, again, very good representation for both models, as we have a coefficient of regression of 0.99 for both models. And then the main difference between the two models is on the pressure drop representation of the solar field, because, as I said, in the simple model, we are considering a rectangular shaped solar field, whereas in the detailed one, we are really representing all the details of the hydraulic of the solar field. So we can see that it makes a big difference on the result of the pressure drop, with a good representation of the pressure drop for the detailed model, but a less good representation of the pressure drop for the simplified model. So what we can say is that for the thermal part, we can go with a simple model if you want just to design very quickly your plant. But if you want to go into engineering details, you probably would need to have a detailed model of the solar field. So to conclude, as I said, the conceptual design phase model of the solar field provides robust thermal result, but cannot be used for hydraulic design purpose. The detailed solar field model offers significantly improved accuracy in pressure loss calculation. And so the further future perspective of this work for each phase of our projects. So for the conceptual design phase, we are trying to finalize the typical config package that I showed you with template-based approach models. For the engineering phase, we are developing more and more detailed models of our components so we can size every component in our plants. And for the operational phase, so we didn't talk much about this phase of our project in this presentation, but we are trying to develop numerical digital twin, thank you, of our operational plants. So lastly, I would like to thank DLR for the development of the TFS library. So as you can see, it's very useful for us to have a robust hydraulic library for our needs. And the ADEM, which is a French organization that helped us develop our project by financial support. I would just like to finish with a saying from George Box. So when you do modeling, you have to keep in mind that all models are wrong, but some are useful. So we have this in mind at NewLib. Thank you.